So here's our next proof. In our next proof, we got a lot of things going on. So again, I'm not even worried about the base case. I'm not worried about the induction step yet. I'm just looking at the problem going, okay, what do we got in here? We got division. We obviously got multiplication, which shouldn't be too bad. But I have a summation. That should sound familiar. And I have a pattern in the summation that really looks familiar, which is our I squared. So I bet I can do something with a formula that you and I know of in summations. Sounds familiar, doesn't it? Now you know why we did that one before this week. But anyway, so that's what we got going on here. So let's look at the base case. The base case, again, all I'm doing is putting in ones into all of the spots where n is. And remember, there's nothing here in the problem that says I can't use 1. There's nothing in here that says n has to be greater or equal to 0. That's one that you might see. Or that you may see that n is greater than 2 or 3 or maybe 100. Something different. Let's just put it that way. You don't see that in this. So all you see is me putting in ones here. So just putting in ones, we have our 2 times 3 over 6. That's 6 equals 6, so that equals true because 1 does equal the fraction of 6 divided by 6, which is 1. So the base case is done. Let's move on from there. Next is we got to do some assuming, and we need to show something. Let's put it that way. Our first part, you're going to always see this is true for n equals k, show true for n equals k plus 1. So we're going to assume that because of our base case that these two are equal, and that's exactly what that one is saying right there. So again, nothing crazy. But notice the assume now uses k instead of using n. So our next part's going to look probably weird at first, so bear with me here. There's going to be 2 spots that are really important. Show, but reduce is actually going to really make sense here in a moment. So we haven't gotten there yet, so bear with me here. Show is going to say that, hey, I want our original equation, but now I'm adding k plus 1 to both sides in order to see if they really are equal to one another. Now this side the right-hand side makes a heck of a lot of sense because all I'm doing is adding, wherever I had n is now k, and I'm adding k plus 1. So that's where you're seeing all that. That part shouldn't be too bad. It's the other side that's interesting. Well, first part is this, and then the second part is I'm going to replace that I eventually with my k, because you can exactly see where the k is popping up here, and have k plus 1 squared because that's what my I originally was going to be. Now, how am I going to do that is my next reduce. Because what I'm going to do is that I am going to get rid of, I shouldn't say get rid of, but I'm going to replace that overall summation that you and I know and love with the equation that we know it's equal to, plus our k1 squared, and then the other side, which I haven't done a manipulation with quite yet. You've seen this replacement in this. That's how I can get away with doing that. And notice, by the way, this makes it, wow, that's divided by 6, and that's divided by 6. That seems kind of, geez, that's not a coincidence. But anyway, serendipitous? Yeah, neither one. Anyway, so that's what I'm going to start doing when we get into our reduce, is now starting to basically factor things, reduce, lowest common denominator, all that stuff you're going to see next. So our next part after the factoring part is I continue to work on the right-hand side of after I've gotten my FOIL, I went ahead and multiplied that entire set together to get this crazy amount of stuff here that I really haven't reduced yet. That's really the next side. So again, multiplied these two things together to get this whole crazy set, and then just went ahead and reduced some of those by adding them together or subtracting out, so it's all addition there, and go ahead and put them all together here. So that's how we come up with the 2k cubed comes from the k squared times the 2k. The 2k plus, it's going to be 6k, came from the 2k times the 3. So there's a lot of things in there on multiplication on how we got that top set. And then I go ahead and reduce that set as much as I could. The last part that you're going to see is getting our lowest common denominator, because I can't go any lower than this. I still have that k plus 1 squared. That's still being a pain. So I need to multiply everything by 6 in order to go ahead and get rid, or frankly have that k plus 1 share in everybody else's love, as I'll call it. So we're using our lowest common denominator here, and when I multiplied everything by 6, this is my first line that I get for everything. And notice it's still that 3k time plus k squared. All of that is in there because I get rid of the fraction part of 6, as you see it getting crossed out here. Same thing for this side. So notice this side didn't change much at all, except for that division of 6. The only thing that really changed was that k plus 1. Now I had to multiply that with the 6, so I have the 6 in front of the k plus 1. That's also why you see me go ahead and kind of, well, frankly, pull that out as well, because I'm going to try to do here in the next line is the k plus 1, which was squared. I'm going to try to go ahead and manipulate that so I can do some easy, frankly, multiplication with that 6 now, k squared plus k plus 1. Finally, go ahead and get a long set together here. And notice I've finally got lowest common denominators. Everything's in cubes or squares, which kind of matches with one another. And that's how I get to my next line, is frankly just doing the math that I have here. And they both end up matching again, thankfully, with a lot of manipulation. So notice again with this left-hand side and right-hand side, there is a lot of work to it. I'm not going to lie to you. But they usually seem to work out. And again, your overall goal is trying to make them be equal on both sides. So you know how to make an equation equal on both sides. Subtract one, add the other, or both, well, either that way. But because we've got both of them equal, then there we can say that the I squared summation does equal that equation that we've got right here on the right-hand side. So we have another one done, using left hand and right side to match one another. Yes, it was a lot of work. And again, if there's a certain spot you want me to go over with you, I'd be happy to do that, but let me know. But hopefully I spelled out all the math for you. I hope.